0.95%. That's the number. No headline attached to it yet. Just sit with it for a second, because by the end of this video, you'll understand exactly why that fraction matters, and why the object that produced it is already beyond Jupiter and never coming back. Atlas passed its closest point to Earth in December 2025. It swung around the sun, lost 13.5 million metric tons of water in a single month, and is now accelerating out of the solar system on a trajectory it will follow forever. The window to observe it with instruments sensitive enough to read its chemistry is closing. By 2028, even the James Webb Space Telescope won't have the sensitivity to reach it. We got one pass. And in that pass, 3 independent research teams measured something that doesn't fit cleanly into the models we use to explain where objects like this come from. To understand what 0.95% means, you need a baseline. Deuterium is the heavier isotope of hydrogen. Regular hydrogen has 1 proton. Deuterium has a proton and a neutron. That extra neutron makes it roughly twice as massive and gives it distinct chemical behavior that instruments can detect from hundreds of millions of kilometers away. It was forged in the first 20 minutes after the Big Bang, during a brief window when the universe was dense and hot enough for nuclear reactions. Once that window closed, the ratio was fixed. Roughly 1 deuterium atom for every 40,000 hydrogen atoms. That number is preserved in the Sun, in Jupiter, in any body that formed from the original material without significant processing. Earth is a slight exception. The ratio here is closer to 1 in 6,500. Because the lightest hydrogen atoms escaped the atmosphere over billions of years and deuterium stayed behind in the oceans. That's a gravitational sorting artifact, not a formation signature. Comets in our solar system carry deuterium-to-hydrogen ratios between 0.01 and 0.06% in their water ice. That range is well established across dozens of measured objects. It reflects the conditions under which they formed: relatively warm, relatively metal-rich, geologically recent in galactic terms. Here's the part that matters. When water ice freezes in deep space, the deuterium-to-hydrogen ratio gets locked in. It doesn't drift. It doesn't equilibrate. Whatever the ratio was at the moment of formation, that's what you read billions of years later. It's a timestamp baked into the chemistry of the ice itself. Deuterium is also, not coincidentally, the primary fuel candidate for fusion energy. The deuterium-tritium reaction, deuterium fused with tritium, has the lowest ignition threshold of any known fusion pathway. It's the reaction ITER is designed to achieve. On Earth, we extract deuterium from seawater relatively cheaply. In the cosmos, its concentration is set by physics that predate every star in the sky. Now, what James Webb Space Telescope read in 3I Atlas? In December 2025, a team led by Martin Cordiner at NASA Goddard pointed James Webb Space Telescope's near-infrared spectrograph instrument at 3I Atlas and measured the deuterium-to-hydrogen ratio in the water vapor coming off the nucleus. The result? The deuterium-to-hydrogen ratio equals 0.95, plus or minus 0.06%. That's not a rounding error. The Sun sits at 0.0025%. Every comet we've ever measured in our own system sits between 0.01 and 0.06%. 3I Atlas comes in at 0.95, 16 to 95 times higher than any solar system comet, and 12 standard deviations above the mean deuterium-to-hydrogen ratio found in protostars across the galaxy. The Cordiner paper, submitted to Nature in March 2026, describes this as extreme isotopic signatures. The authors, 19 of them, from JPL, European Space Agency, Paris Observatory, do not hedge on the measurement. They hedge on the interpretation, which is different. Their explanation: 3I Atlas formed at temperatures below 30 Kelvin, in a metal-poor environment, early in the galaxy's history, roughly 10 to 12 billion years ago. That is the natural explanation. And they say so plainly. It's a preprint. It hasn't completed peer review. The numbers could shift. Unlike any solar system body. That phrase is in the abstract. That was water. Then, 3 weeks later, a separate team published a second result. Nathan Roth at American University using ALMA, the Atacama Large Millimeter/Sub-Millimeter Array in Chile, measured the deuterium-to-hydrogen ratio in a different molecule entirely, methane. The result, 3.31, plus or minus 0.34%. 1 deuterium for every 30 hydrogen atoms in the methane coming off this object. The authors call it an exceedingly rare detection of deuterated organic molecules in an interstellar object. That phrase isn't editorializing. That's the paper's language. 2 different instruments. 2 different teams. 2 different molecules. Both measurements pointing in the same direction, by roughly the same order of magnitude above anything in our solar system. Roth described the observation as like taking a fingerprint from another solar system. He wasn't speculating about what the fingerprint means. He was describing what the data looks like. Does that pattern seem unusual to you? Or does it resolve into something simple when you add the third measurement? The Very Large Telescope in Chile, ISO's facility in the Atacama, using the UV spectrograph, tracked the isotopic ratios of carbon and nitrogen in 3I Atlas, not in water or methane, but through the cyanide molecule in the coma. The team, led by Cyrielle Opitom at the University of Edinburgh, found a nitrogen-14 to nitrogen-15 ratio of 343. Solar system comets average around 150. The carbon ratio, carbon-12 to carbon-13 equals 147, sits above typical values as well. Their conclusion aligns with Cordiner's origin in a metal-poor environment, 10 to 12 billion years ago. 3 independent teams, 3 different instruments, 3 different molecules, water, methane, cyanide. 1 consistent answer about the epoch of formation. Our sun formed 4.6 billion years ago. This object formed more than twice that long ago. The star it came from almost certainly no longer exists. Whatever planetary system it was part of has had 10 billion years to evolve into something unrecognizable, or to collapse entirely. We caught a piece of it. There's a mundane explanation for all of this, and the researchers who measured it say so. Formation in an extremely cold, early galaxy environment can naturally produce elevated deuterium-to-hydrogen ratios. The chemistry works. The models accommodate it. Almost certainly, that's what happened. But A.V. Loeb, former chair of Harvard's astronomy department, founding director of the Black Hole Initiative, and a physicist with enough institutional weight that his questions get taken seriously, even when his conclusions get rejected, published a blog post on March 24, 2026, and ended it with a single sentence. Since deuterium is fusion fuel, might its overabundance in 3I Atlas flag a technological signature? He didn't answer it. He published the question and stopped. His colleagues largely disagree. The consensus position is that the chemistry is natural. Loeb is a controversial figure. His previous claims about Oumuamua generated significant pushback from the community. And this observation is no different. Most researchers find the natural explanation adequate. But the question is out there, from someone with the credentials to ask it formally. And it hasn't been answered. The deuterium isn't the only reading that requires explanation. James Webb Space Telescope's near-infrared spectrograph instrument, observing 3I Atlas in August 2025, when the comet was still 3.32 astronomical units from the Sun, found a carbon dioxide to water ratio of 7.6, plus or minus 0.3. That's 4.5 sigma above the trend for solar system comets. The most probable explanation involves galactic cosmic rays. Over billions of years in interstellar space, high-energy particles convert the outer layer of the nucleus, roughly 15 to 20 meters deep, transforming CO into carbon dioxide and building an organic crust. That model fits the data reasonably well. The problem is that we've only ever seen that crust. Every instrument that observed 3I Atlas was reading the processed exterior, the pristine interior. Whatever the object actually looks like underneath has never been sampled. Not once. ALMA also found methanol to hydrogen cyanide ratios between 70 and 120 in the coma. Solar system comets typically run between 3 and 5. The methanol was coming from two sources simultaneously: the nucleus and from icy grains suspended in the coma itself, which is atypical behavior. No established mechanism explains the distribution. And the Very Large Telescope detected neutral nickel in the coma. Iron was not detected. In solar system comets where nickel appears, iron usually appears alongside it. They're co-released from the same dust grains under the same thermal conditions. How nickel separates from iron here remains unresolved. Each of these, in isolation, is probably mundane. The galactic cosmic ray model handles the carbon dioxide. The methanol may reflect unusual formation conditions. The nickel decoupling might be a grain chemistry effect nobody has fully characterized yet. But you're now looking at 4 separate chemical anomalies in one object, each with a plausible explanation, and none of those explanations fully confirmed. 9 days after perihelion, its closest approach to the Sun on October 29, 2025. SOHO's SWAN instrument began tracking 3I Atlas by mapping the hydrogen cloud expanding around it. SWAN detects Lyman alpha ultraviolet emission, which traces the hydrogen atoms released when solar radiation breaks apart water molecules. The team ran the observation for 32 days. Their estimate: 13.5 million metric tons of water released in 1 month. The peak production rate, measured on November 6th, was 3.17 times 10 to the 29th molecules per second. By early December, it had dropped by more than an order of magnitude. 13.5 million metric tons of water, carrying a deuterium-to-hydrogen ratio that has no parallel in our solar system, released into interstellar space over 4 weeks, and now dispersed irretrievably across the void between stars. We measured it once. We can't go back for it. The papers themselves document the open problems. Loeb has raised a temperature constraint that hasn't been resolved. Protoplanetary disks cannot be colder than the cosmic microwave background radiation at the time they form. At the redshift corresponding to 10 to 12 billion years ago, around Z equals 10. The cosmic microwave background temperature was approximately 30 Kelvin. That is precisely the temperature threshold the natural explanation requires for producing deuterium-to-hydrogen ratio equal sign 0.95%. Whether that's a coincidence or a limit on the model is an open question in the published literature. There's also a mass budget problem. If 3I Atlas-type objects originate from metal-poor stars, the number density of such objects implied by the detection rate, combined with the estimated nucleus radius of roughly 1.3 kilometers, implies a total mass in interstellar space that significantly exceeds the heavy element reservoir available in low metallicity stellar populations. Either the radius estimate is wrong, or the number density is wrong, or the origin model needs revision. No resolution has been published. And the interior of the nucleus remains completely uncharacterized. Everything measured, the deuterium-to-hydrogen ratios, the carbon dioxide, the methanol, the nickel, came from the outer 15 to 20 meters of processed surface material. Whatever is below that layer has never been exposed to any instrument we've built. The object is currently beyond Jupiter's orbit. By 2028, it will be beyond James Webb Space Telescope's detection threshold. The measurement window is closing. The interior question will not be answered. We've now seen 3 confirmed interstellar objects pass through the solar system. Oumuamua in 2017 had no coma. It accelerated without any visible outgassing, at a rate that still has no consensus explanation 9 years later. Its shape was unlike anything in our catalogs. Borisov in 2019 looked like a comet, active, icy, structurally familiar. High CO relative to water. It fragmented after perihelion. Astronomers called it reassuringly normal. 3I Atlas is the most chemically characterized of the 3, and the least similar to anything that formed here. The deuterium anomaly, the carbon dioxide excess, the methanol surplus, the unpaired nickel. 3 objects. 3 completely different profiles. If anyone assumed that interstellar objects would cluster around some average composition, that assumption is now gone. What we're looking at is a sample space of 1, repeated 3 times, and each time the result is different. We are at the very beginning of the statistics. Here is the current state of the record as of March 2026. 3 independent research teams, using James Webb Space Telescope, ALMA, and the Very Large Telescope, measured deuterium-to-hydrogen ratios in water, methane, and cyanide that are unlike any solar system body. 2 of those papers are preprints, not yet through peer review, numbers still subject to revision. The 3rd measurement from Very Large Telescope is submitted to Nature. None of them claim the object is artificial. All 3 conclude, probably natural, formed in extreme cold, early in galactic history. Avi Loeb asked a question in public and didn't answer it. The interior of the nucleus has never been observed. The object is moving away at 68 kilometers per second. The window for the most sensitive observations closes in approximately 2 years. So, 3 instruments, 3 teams, 1 anomaly across 3 separate molecules, with a plausible natural explanation that has 2 documented open problems embedded in it. Where, in your view, is the line between probably natural and requires a different explanation entirely? That's not a rhetorical question. It's the actual boundary the data is currently sitting on.